Brilliant. Thank you, Tim. It's nice to be here. It is quite a daunting brief to talk about everything that's ever happened and will happen in less than an hour. Hopefully, I don't overrun. So, just to introduce myself quickly, I am a teacher at the university as well as a PhD student. So, my research actually looks at pulsating stars. So, I'm an astroseismologist. So, astro for stars, seismology for things like Hubble. And I use the light from these stars to understand what the interior of the stars are doing. I'm not going to be talking about any of that today. I'm going to be talking about the entire history of the universe. I'll try and move this out of the way. Move this, perfect. So we're going to start by looking at the early universe. How do we know that the Big Bang happened? So we know broadly that it was the beginning of our universe, and we know from a few pieces of evidence roughly how it happened. So we're going to talk a little bit about that for the first half, and then we're going to pivot to the structure of the universe as it is at the moment, and then we're going to talk about how it ends. It is a bit of a bleak ending, I'm afraid, but fortunate for all of us, none of us will see it, so it'll be fine. So, perfect. We know that, or I'm assuming most of us know, the universe began with a big bang, right? 13.8 billion years ago. This is where everything began. This is where matter came into being. This is where time itself came into being. This is where all the fundamental forces came into being. So every single aspect of the universe that we can describe with physics came into being at this singular point in time, 13.8 billion years ago. Take my word for it, and I can finish now, or we could go into a bit more depth if you like. So, how do we know this? What is it? What evidence have we got that tells us that this is actually true? Well, funnily enough, it's 100 years ago, roughly, since we started to glean what was going on. About 100 years ago, we made some discoveries about the nature of our universe. So before 1924, we didn't really know that there was anything else beyond our own galaxy. So our galaxy, our collection of stars, is called the Milky Way. We could measure roughly how big it was, and we could see other fuzzy patches of stuff in the sky like this. Anyone know what this might be? It is Andromeda. So 100 years ago, that's what they looked like to us. We didn't know what it really was, just thought it was another fuzzy, inverted commas, nebula, right? Until someone else came along, Edwin Hubble, very famous name, who pointed his big telescope, the most powerful telescope at the time, in 1924, at Andromeda, and discovered in actuality it is a galaxy unto itself. He discovered something with the help of somebody else who doesn't really get any credit. Henrietta Swan was the person really more responsible for his discovery, because she discovered a subset of stars, pulsating stars, like the dancing ones that I look at, called Cepheid variables. And these stars pulsate and jiggle and dance in a very structured way, such that we can use them as standard candles, which means if one of them pulsates in a certain way in our galaxy, it will pulsate in the same way in a different galaxy. And because it does that, we can basically map its light output and understand how bright it is at point of source. What Hubble did was find some of these Cepheid variables in Andromeda, and he realized it wasn't part of our galaxy at all. In fact, it's an entirely separate galaxy, and it's 2 million light years away. Our galaxy is 100,000 light years across, so to discover something 2 million light years away, it was quite a startling thing, right? It made our universe suddenly a lot bigger. He pointed his telescope, I should say, by the way, to begin with, all these links in these slides, there's little links in the corner of every slide. If you are interested in anything I'm saying, these slides are available, and it gives you like a jumping off point if you want to go down the rabbit hole and find any interesting information. So these slides will be available to you afterwards. There's a particularly nice picture of Andromeda taken by the Hubble Space Telescope, named after Hubble, where you can zoom in and resolve these individual stars in Andromeda in a way that was not possible 100 years ago. So it's quite a cool thing. So it's worth clicking those links anyway. So to continue the story, Hubble pointed his telescope in many different directions. I don't want a tiny sip of wine. He pointed his telescope in every direction, using all the different methods to glean distances as well. And he realized something with the help of a few other people. He realized that whichever direction we're looking, when we see galaxies, these galaxies are receding from us. They're moving away, barring the very closest ones to us, our neighboring galaxies like Andromeda. They're gravitationally bound to us, but everything else further away seems to be moving away. What's more, his law that he put together based upon his observations, and this is his graph from 1929, tells us that the further away we look, the faster these galaxies are moving away from us. So we're looking in every single direction, we're seeing galaxies, and we're seeing them moving away from us at ever more rapid speeds the further away we look. A key thing to note at this point is it's the space between the galaxies that's expanding. The galaxies are moving away from us. Space is expanding, but the galaxies themselves are not. We'll come to that in about 40 minutes as to why that is the case. But space itself is expanding, as Hubble seemed to note. The galaxies seem to be moving away from each other, and it was an interesting thing. If we take this and reverse engineer it, the implication must be that everything is moving away from each other. Surely, at some point in the distant past, everything must have been more compact. If everything is expanding, moving away, if we go back in time, there must have been a more compact configuration of the universe. Everything must have been closer together at some point. And we can use Hubble's observations and the more recent observations that have been happening over the last 100 years to plot a graph just like Hubble's. If we go back to this one, we've got a more modern version of this graph with millions upon millions of galaxies on it, looking all the way back towards the beginning of time. When we take the curve of that graph, it's a very simple equation. We can just find the inverse and find what we call the Hubble time. Now, it's slightly skewed from the number on here. It's the Hubble time. It's slightly different. If you were to ever Google it, you'll find out why it's slightly different. But it gives us basically the age of the universe. So if we extrapolate backwards, everything's expanding. Going backwards to when everything was slightly more compact, 13.8 billion years ago is that time when it all must have been squashed together at its most compact. So that's what we think. We think 13.8 billion years ago, everything was squashed together in this compact configuration, and that's what we call the Big Bang. And it all started because of Hubble's observations 100 years ago. The Big Bang itself, or the idea of a Big Bang, the idea of this moment of creation, if you like, this moment of birth of the universe, wasn't actually Hubble's. It was George Lemaitre on the left here. So he was a Belgian priest. If you ever Google the Big Bang, the Big Bang Theory, apart from an awful American sitcom, you will find a lot of information about George Lemaitre. He was a really, really interesting person and is worth reading about. He was a Belgian priest and part-time astrophysicist. And he suggested that the birth of the universe would have been this kind of explosive, if you like, instigation, this moment at which everything just came into being. And George Gamow on the right here was also a main proponent of this. He took Lemaitre's ideas and expanded them and started to suggest ways in which this may have happened. So Gamow and Lemaitre are the two kind of big forefathers, if you like, of the Big Bang theory. The Big Bang itself, as a name, by the way, wasn't coined by these two people. And if you think about it, the Big Bang doesn't sound very scientific. It doesn't sound like a particularly scientific way that anybody would describe anything to do with the universe. Lemaitre himself favoured the primeval atom, this idea of everything coming from this one individual pregnant point in space and time, which I think is a little bit more poetic. Big Bang was coined by this chap here. Has anyone come across him before? Yeah. Famous Stoic Yorkshireman from my neck of the woods near Keighley. He was a fantastic physicist. His contribution to stellar physics especially was monumental. But he was also a bit of a grumpy bug. He didn't favour this idea of a Big Bang at all. He coined the term Big Bang as almost a pejorative, really. So he was doing an interview on BBC Radio, I think in 1949. He favoured what is called a steady state cosmology, this idea that the universe has always been what it is, and the fact that we see it expanding doesn't say anything about a Big Bang. It just means that it's been going forever and it's been replenished. That was his favourite. And he said the words Big Bang as almost a kind of an insult. That's why it sounds a little bit strange, the word Big Bang, but it stuck. And it didn't really come into favour as a descriptive term for this whole thing until the 1970s or 80s. But it is now the way that we describe the birth of our universe. And kind of like the idea of him looking back and thinking, oh, I should have never said that now. Well, never mind. So we've got this idea. We've got this idea that started with Hubble in 1929. The universe is expanding, and it's expanding. We had Lemaitre and Gamow suggest that there's this almost strange, infinitesimally small point from which it stems, and we've got Fred Hoyle giving it a derisive name. What other evidence do we have for the Big Bang, right? It's all well and good me just saying, oh, we can see the universe expanding, but from where is it expanding? Well, one of the biggest pieces of evidence that we've got, or at least this very dense initial configuration of the universe, is this. This is one of the biggest and most famous images in modern astrophysics. Has anyone seen this? It's quite a, it's not a pretty picture. It's not a Hubble Space Telescope picture of a galaxy or a nebula or anything like that. But what it is a picture of the very first light in the universe. It is almost, it's kind of romantic to think, almost biblical, the first light. What we mean by this is, if we extrapolate backwards to the point at which everything was all compacted down, stars, galaxies, all the dust, all the other stuff that makes up a universe. If we think about it, if we're compacting it all down and down and down, it becomes denser, more compact, hotter and hotter and hotter, to the point where everything is basically just a giant plasma, this state of matter where atoms are stripped of their electrons and it is this big mass of plasma, like the sun is a plasma, effectively, all stars are plasmas. The idea is that when everything is so compacted down at the beginning of the universe, or near the beginning of the universe, there wouldn't have been any stars or anything just yet, because it was all so squashed down. And in that situation, everything would have been super dense, super hot, and it would have been a plasma, and it would have been opaque to light. Light finds it very difficult, photons find it very difficult to travel through plasmas, pardon me, like this. In the 1940s, George Gamow and friends suggested that we might be able to see this early configuration, or at least the end of it, if, as he hypothesized, this early superhot plasma existed. There would have come a point where it stopped existing, where the universe expanded to a sufficient degree that the universe cooled, the plasma cooled, and the atoms were no longer delocalized from their electrons, and the electrons could come together with the nuclei, and light could suddenly pass through it. This was his idea. This idea that there would have been a first light. And for about 10, 15 years, they were looking everywhere for it. And the discovery was actually a complete accident. This is a picture of a telescope called the Holmdel Horn Antenna in the USA. It was used by two astronomers called Penzias and Wilson, who won the Nobel Prize in 1974 for their discovery of the CMB, cosmic microwave background. It's a fairly well-told story. I'm sure some of you might have heard this before. They weren't aware of what they had found. They weren't really looking for the CMB. They were just pointing their feed horn, as it looks like, the kind of thing that you put in your... I like the idea of it looks like one of those ear horns that was used 50 years ago when they were listening to the sky. They were looking for other things. And they kept hearing this hiss, this strange hiss, this strange static, this strange background noise in their data. No matter where they point their telescope, they were doing everything to try and get rid of it. They were going into the kitchens in the observatory, turning off all the electronics, turning off all the kettles. They went into the feed horn itself and swept up all the bird poo with a brush, thinking that might have been what's causing it. They had no idea until someone pointed out it's an intrinsic part of the signal that they're picking up. It's everywhere in the universe, and in fact, it is the background noise of the universe. It is the background noise of the first light of the universe. Redshifted, because of the expansion of the universe, down to about 3 Kelvin, so 3 degrees above absolute zero. And that is what they had discovered. As I say, this was about 380,000 years after the Big Bang, based upon our model, based upon our theory. We think this first light occurred about 380,000 years after the Big Bang. When it was emitted, when plasmas become transparent to photons, to light, it is around 3,000 Kelvin. So we think at this time, the universe, all of it, there's just this big collection of stuff, was about 3,000 Kelvin. The cosmic microwave background now is about 2.8-ish Kelvin everywhere, the entire universe. It's everything. The entire universe is this temperature at this background level, which means the universe has expanded so much that it has redshifted. The wavelength of the light has shifted from 3,000 Kelvin down to just 3 Kelvin, close to absolute zero, which is mind-boggling that we can detect it. They detected it in 1965 with their equipment. Since then, we've got all sorts of very advanced pieces of kit, which allow us not only to measure it, but we can also measure tiny temperature fluctuations within it. So it's 2.75 Kelvin, but within that we can find microscopic variations. And if we model and backwards engineer our current iteration of the universe backwards, we can see, we think, the initial seeds of structures in the entire universe from this. So over dense areas in the CMB, where it was slightly hotter or slightly colder, would tell us that there were areas that were slightly denser or slightly less dense, that would then feed and seed the stems of galaxy formation and structure within the universe itself. This is a model of exactly what I've just described. So starting with the CMB at about 380,000 years after the Big Bang and extrapolating forwards, we think this is how it might have evolved. So we can see these beginnings of structure in the cosmic microwave background. So we have got evidence that the universe is expanding. We know it is expanding. Everywhere we look, the galaxies are moving away from us. We've got evidence of a first light in the universe. We know that the universe was at an earlier, more compact configuration, and it was 3,000 Kelvin, and we can see it. We know it was there, and it was 13.8 billion years ago. So those are two things that we can observe and see. So with that in mind then, what happened before that? What do we think actually was the Big Bang? What happened in this moment of birth? Well, a lot of this comes down to modeling. A lot of this comes down to our ability now to use our quite substantial scientific technology to use things like the Large Hadron Collider, nuclear experiments here on Earth to mimic what we think the conditions may have been in those early periods. We know what happens in the plasma. We can do these things in simple school laboratories in terms of something that's 3,000 degrees. We can mimic a plasma. We can go to the Discovery store and get like a little toy with some of these plasmas in them, right? We can do stuff like that. We can build these huge particle colliders. We can do all sorts of experiments that, funnily enough, allow us to shave off different components of the Big Bang down to about 10 to the minus 36 seconds after we think it happened. So that's a trillionth of a trillionth of a trillionth of a second after the Big Bang. The science that we do is basically the science of what happens when things get hotter and more dense. And the Large Hadron Collider in particular, but other things as well, allow us to mimic these conditions. We can make things that are trillions of degrees for a fraction of a second. We can make particles pop in and out of existence in the Large Hadron Collider. We can combine particles, smash them together, and recreate the conditions that we think happened in these early years. So even though we can't see it, and even though it does sound a little bit strange and conjecture in some terms, we have been able to measure these things and observe these things. And there are components of this model that predict certain other things that we are now trying to find, which I'll come to shortly. So what we do is basically recreate these conditions. We always get asked this question of what actually happened before the Big Bang, what started the Big Bang. I'm not here to answer that, I'm sorry. Who knows? But what I can say is what happened in that moment and how it may have taken place and what the actual order of operations would have needed to be for us to exist in this universe, in this room now, what we think must have happened in the exact order it should have happened to create the universe that we live in. The nicest way of deflecting the question of what started it and where it comes from, I think, is from Stephen Hawking, who just kind of gives one of these nice waffly answers that you always give to these kind of things. It says, well, you can't keep going south if you go past the South Pole, right? Who knows what happens after the Big Bang or before the Big Bang? We don't know. This is a question that we will hopefully find answers to in the future, but at the moment, there is no way of determining what that case was. So as I said, we can pick up this story about 10 to the minus 36 seconds after the point, right? There's reasons for this. We think these things have to happen in this specific order. Usually when I give these talks, I explain scientific notation, just in case. So people who, I know a lot of doctors who do numbers and stuff. So just in case, this is 0.00000 with 36 zeros after it, seconds. Just for comparison, if you time from the Big Bang to now in seconds, that's 10 to the 17 seconds. So we think we can shave off in the other direction even smaller in terms of how much time we can pick away at the birth of the universe. A really important thing to discuss as well is, I think it was Bill Bryson in one of his books, he described it as like, it is not a pregnant point in space that explodes. It's very easy for us to visualize a dark, empty room with a bulb that flashes on and suddenly the universe exists and it explodes outwards. It isn't that. It's the entirety of the universe coming into being all at once. It isn't expanding into anything. It is the universe itself coming into being and expanding. It's expanding everywhere all at once. We are still in the Big Bang. It is still happening. We are still part of it right now. We are riding the wave of the Big Bang as the universe expands. So it didn't happen in a little spot and then expand into something. If there is an edge to the universe, we don't know where it is. We don't know what's outside of it. Another waffle answer, I'm sorry, but we don't know. But we do know that the configuration of the universe and the one that we live in right now began in this infinitesimally small point called a singularity. We model this before our real science begins. So before 10 to the minus 36, we assume that there had to be what is called an inflationary period. For our universe to exist in the state that it exists, which we call a flat universe, there's different descriptions of the geometry of the universe. I won't go too much into this because it's boring, but there is the idea of a flat universe, a curved universe. We think we live in a broadly flat universe. And for that to be the case, there needed to be, this sounds ridiculous, there needed to be, we'll get to the real science there. This needed to be this inflationary period where the universe was expanding faster than the speed of light for the first, 10 to the minus 40 to the 10 to the minus 36 seconds. We can't measure this, we can't observe this, but we are looking for the signature of this. Some of you might have seen in the news over the last 4 or 5 years, gravitational wave astronomy has taken a bit of a leap. LIGO is this piece of equipment, this giant interferometer that is searching for these waves that are propagating, traveling through space. They are the signatures of monumental collisions. We can measure stars colliding with each other, black holes colliding with each other, and they cause ripples in space-time, predicted by Einstein's general relativity. If this happened, then there would be a signature in the universe that we will be able to measure. However, we would need interferometer about half the size of the solar system to measure it. There's an idea to build one. So they're going to build 3 satellites, 3 probes that will park themselves at different points in the solar system and have lasers between them and hope to try and measure these waves. It's probably in the far-flung future. Someone's going to spend some money on it eventually, but it's not beyond the realms of possibility to try and find these gravitational waves from this monumental inflation period at the very beginning of the universe. At this point, at about 10 to the minus 36 seconds, when it's inflated very briefly, this is where science takes over, and we can fairly surely say we think this is the order we think started to happen. The first thing that probably happened was quarks and antiquarks came into being. So these very tiny particles that form the basis of the standard model of physics. So we know that atoms are made up of protons and neutrons. We know that protons and neutrons are made up of quarks. And there's a whole sea of other particles, like the Higgs boson was famously discovered about 10 years ago. There's a whole host of them, about 15 or 20 of them. We think at about these temperatures, just before protons and things start to come into being, quarks and antiparks and other standard model particles come into being. Before that, there were no particles. It was too hot. At the temperatures that we're talking about here, 10 to the 33 Kelvin, all physics breaks down. We can observe this breaking down. If we try and accelerate too much, too fast, too hot, physics breaks down. We've got 4 fundamental forces. We've got gravity, strong and weak nuclear force that binds particles together, and we've got electromagnetism. At these temperatures, those forces do not exist. At these temperatures, particles do not exist. Matter does not exist, just energy. Once it drops below 10 to the 33 Kelvin, we start to see particles coming into being and the forces starting to come into effect. If we've got particles, there will be forces taking place between them. So the first forces start to come into being about 10 to the minus 36 seconds after the Big Bang. Quarks start to come into existence. And then about a millionth of a second, a breezy millionth of a second after the Big Bang, these quarks can start to come together to form things that we're a little bit more familiar with. And scientists at CERN, scientists at all sorts of other grand experiments around the world, devoted entire careers to shaving off milliseconds and tiny aspects of this that I'm talking about in a matter of seconds, right? Like, people have dedicated lives to this, and they're fairly certain that the order that things happened in this way. They know, for example, the order that the forces have come into being. Strong and weak nuclear force first, followed by probably electromagnetism, followed by gravity. We know that it had to be quarks and leptons and all these things coming in this order into protons and neutrons. So once protons and neutrons come together, we start to get to things that we're more familiar with. We start to then get to a point where we can have what we call nucleosynthesis, which basically is a fancy way of saying we can start to get atoms. Yeah. So the first 3 or 4 minutes, I'm just going to mute something if that's okay. Just I don't want to Noise in the background because it freaks me out. There we go. Big Bang nuclear synthesis. Nuclear synthesis is a fancy way of saying atoms coming into being. Most of the stuff that we are made of, the vast majority of stuff that we are made of, came from stars, stellar nuclear synthesis. All the other stuff, which I'm saying, all the other stuff, the vast majority of the atoms in the universe, and still the vast majority of the atoms in the universe, is hydrogen and helium. In the first 3 or 4 minutes of the universe, these protons and neutrons will have come together to form hydrogen and helium. About 3 minutes after the Big Bang, all of that stuff will have taken place. Now, a really strange thing to think is there was no more massive atoms, no bigger atoms than hydrogen and helium for millions and millions of years after the Big Bang, barring maybe a tiny little amount of lithium. It was just hydrogen and helium. Everything else, lithium, carbon, all the way up to iron, and then all this other heavy stuff, the stuff that we're made of, was made in stars. It was Carl Sagan that said, we are star stuff, and he wasn't kidding. All the stuff that means things to us, planet Earth, all the rock, all the silicon, made in stars. At the Big Bang, just hydrogen and helium, and a tiny bit of lithium. 25% roughly helium, 75% roughly hydrogen. The way this happened was neutrons tend to decay into protons very, very quickly. So if there were no neutrons left after about 3 or 4 minutes, there weren't going to be any neutrons, which means we were stuck with hydrogen and helium. That's why we've got 25% helium, 75% hydrogen. The reason why we don't have anything more massive than, I think I've got a slide of it, something like this. The reason why we don't have carbon, oxygen, iron and things is because, funnily enough, it requires higher temperatures to fuse these things. In stars, to get to iron, the core of a star needs to be millions and millions of degrees. But by this point, the universe has already expanded beyond that and it was too cold. So it's a chicken and egg thing almost. In order to get protons and neutrons, the universe needs to cool down to a certain degree. And then to fuse them into anything heavier than helium and hydrogen, it needs to be hotter again. And it wasn't getting hotter for a long time. So all we could get was hydrogen and helium at this beginning stage. To get it any hotter, we needed stars. And they didn't come around for a fair old while. This is a key necessity, by the way, of the Big Bang theory. This order that things happen, this rough approximate 3 or 4 minute period in which nucleosynthesis, Big Bang nucleosynthesis was just happening so fast. It's a key necessity of the observations that we see of our universe. It's a strange thing to think that out there in the cosmos, the vast majority of stuff is contrary to our observations here on Earth. 75% of material in the universe is still hydrogen, roughly. 23% is still helium, roughly. 2% is everything else. That everything else is mostly oxygen and carbon. So things like gold, things like iron, anything else made in stars. And the fact that we're on a planet made mostly of those things is just luck, really. Planets are a side effect of star formation. We are lucky to live 13.8 billion years after the birth of the universe because there's been enough time for stars to exist, to evolve and develop and create new material that can then go in the formation of stars. The very first stars, we'll see in a few minutes, were just hydrogen and helium. They couldn't have had planets because there was no detritus, if you like. The fact that the detritus exists after stars die and spew it out means that as successive generations of stars are born and evolve, things like us can exist. So there would have been no life at the beginning of the universe because there couldn't have been any heavier elements created, right? It's a funny way to describe the stuff that we're made of, but we are effectively just a trace amount of, like I say, detritus that orbits around the star. Like the sun is 70-odd% hydrogen, 20-odd% helium, trace amounts of other stuff. The planets around is where all that kind of dust exists, and we are the dust, basically. All that stuff wasn't made in the Big Bang. I've already talked about why there was no heavier elements, right? They were all made in stars later on. And this is where we then get to the atomic era. So we've got these nuclei. We don't have atoms yet, I want to emphasize, because it's still too hot. We've got this plasma, if you like. We've got the nuclei of hydrogen, which is basically just a proton, and we've got the nuclei of helium, which is 2 protons and usually 2 neutrons, right? Electrons are there as well, but they are not bound to the atoms in the traditional way that we understand them to be, because it's still too hot. They are in this big hot soup, this plasma. But as the universe continues to expand, it becomes more diffuse, less dense, and it cools down. and it cools down to a sufficient degree where this plasma can suddenly start to become recombined. Like that's a fancy way of saying the electrons can combine with the nuclei and form atoms. A really interesting kind of pub quiz fact, if you like, the first true atoms in the universe weren't hydrogen, they were helium, because it's easier energetically for an electron to combine with a helium nuclei than it is a hydrogen nuclei. So funnily enough, the first true atoms were probably helium. It took a little bit longer for the electron to combine with the hydrogen. In fact, we're in a relatively breezy 360 odd thousand year period here now from the Big Bang. So we've gone from shaving off billionths of a second to thinking this expansion and this cooling probably took place over a fair old, maybe 380,000 years. Over this period is what we call recombination, where the atoms started to come together, electrons started to come together. And this is where we get to the other end of this tail, where we start to get to this cosmic microwave background, if you remember. This idea that when electrons recombine with their nuclei, it's called recombination, even though they weren't combined before. It's just an annoying term, recombine. It means electrons are joining with their nuclei. When that happens, when they drop down to the lowest energy state, the most efficient energy state, these atoms emit a photon of light. And that photon of light would have been the microwave cosmic background, the very first light. So we know that that exists, we've seen it, and our models previous to that suggest that this is how we got to it, right? Hopefully I didn't go too quick, only a couple of you are asleep. So we think, or we know, in fact, that after this, we have what is called the cosmic dark ages. But before that, we think we had this big atomic soup that was still quite hot, right? 3000 Kelvin, getting a little bit lower, emitting light. So the entire universe, still no stars, still no galaxies, still nothing meaningful that we would recognize in terms of structure that we see in the universe now. Just been a big collection of atoms, a soupy orange glow. So imagine viewing that. It'd be an odd thing, right? Just sitting in a atomic soup. It'd be very hot. You'd burn to death within seconds, but it would be very eerie. This would cool over the course of a few million years as the universe continues to expand. 3000 Kelvin down to cool enough where the light it is emitting is no longer visible. So there are different levels to light, right? We've got our spectrum, red up to blue. As things cool, they emit light. We're emitting light right now. I'm quite hot and warm. I'm emitting light, but it's of a wavelength that we cannot see. As this gas cooled down, it would have stopped emitting light that we can see, to the point where we would have had a universe still with no meaningful structure and with atoms that are now too cool to emit light, which means we've got this cosmic dark age. We can say we can see this. We've pointed to things like the James Webb Space Telescope and Hubble back in these directions. Obviously, we can't see it because there's nothing to see, but we think we've got about 100 million years or so of this so-called cosmic dark ages where nothing is really happening apart from just this collection of cooling atoms. Kind of strange to think. We think at around 100 million to 250 million years after the Big Bang is when stars probably start to form. Areas in this CMB that we saw earlier on where there's overdensities, where there's slightly more hydrogen and helium than in other areas, might start to come together, and some stars might start to form. These first stars would have been absolutely monumental in size as well, because it was just hydrogen and helium. And stellar birth theories tell us that if you've just got those two things, you will have big stars that live fast and die young. Our star, the sun, will live for about maybe 13 billion years in total, so it's not quite halfway through its life yet. These stars, the biggest stars, would have lived for maybe 1 million years, if not less, and they would have done the first stellar nucleosynthesis, started to spit out the first heavier elements, started to create new materials that can then go into the birth and successive lives of new generations of stars, create things like planets, create things like rocks, create things like solar systems. So these first stars would have formed very early on. And about the same time, we would have had the very first galaxies as well. It's a chicken and egg thing. We're not quite sure what came first, galaxies or stars. This might sound odd because surely you need stars for galaxies to exist. But we think the structures that the stars are pinned on in the galaxies might have actually formed around a framework of other stuff. For example, dark matter, or around gigantic black holes, which we're going to get to in a second, but we're not quite sure. But what we can do is build giant telescopes that go up into space and point in any given direction and look for infrared light. We're going to look at some of those pictures in a second. But this epoch, from stars into galaxies, is called the galactic era. And that is the one that we're living in now. It might seem like a big leap to go from 380,000 years after the Big Bang to a couple of 100 million years after the Big Bang to now. But we're going to see in about 20 minutes' time, actually 13.8 billion years is very early in the universe. This is where we live. We live in the galactic epoch. We've got stars, we've got planets, we've got galaxies, we've got structure, and we've got stuff. James Webb is the latest in a succession of incredible telescopes that allow us to see further and further in the past, right? The further we look in terms of space, the further into the past we're looking, right? James Webb thinks, or rather we think, we can see some of the very earliest galaxies. They've redshifted. What that means is their light that they emitted has shifted its wavelength from what would have been blue at the time of emission to red. Again, this isn't because they are moving, although they are moving as well. It's because space itself is expanding. So it's a universal redshift of space itself stretching the light. So we are seeing galaxies, the very earliest galaxies. We think we are seeing ones from about 300-400 million years after the Big Bang, some of the very earliest galaxies. And we can observe them, we can measure them, see how bright they are, understand what light they were emitting when they were first born. We can also use James Webb. We haven't done this yet, but we can also use James Webb to do spectroscopy on them and try to identify the materials that were in those stars and confirm that it is obviously mostly just hydrogen and helium. All those stars are obviously dead now, so we can't see any of them around now, but we can look back in the past using James Webb and see these galaxies made up of these stars. The earliest ones we've found are, like I say, 300 million years after the Big Bang, some of the very first galaxies. And these are just early results from James Webb. If we let it stare for just a few weeks or months, we're going to start to find even more things. At the moment, it's just kind of spinning around, looking at all sorts of stuff, and it hasn't a chance to really do some in-depth things like the Hubble Deep Field, if you've ever seen that, where the Hubble telescope looked at one patch of sky for weeks and weeks. We haven't had James Webb do that yet, but when it does, it's going to find some interesting things. So we can see these things, and we can look back and see the earliest structure of the universe, and we can see it evolve. We can see the evolution of structure in the universe based upon our earliest observations, and we can take steps back from 13.4 billion years ago all the way to the present and see the evolution of structure in the universe. We can see how galaxies came together to form these different structures in the universe. What do we mean by structure? Well, galaxies aren't the biggest level of thing, if you like, in the universe. They live in cities and collections of other galaxies that are getting bigger in size as time goes on, or smaller in size in some cases. So we'll see some of this. What did they form around? I alluded briefly to two things earlier on. I alluded to black holes and I alluded to dark matter. We'll talk about dark matter in a second. But first of all, black holes. We can't really do a discussion of the universe without talking about black holes. There are three different kinds of black holes that we know. Black holes are these things that are predicted by Einstein's relativity. Again, most things are. And they are areas of space-time where gravity is too great for anything to escape, right? Light cannot escape. That's the standard definition of a black hole. Most of them are formed, most of the ones that we know of are formed from the death of very, very large stars. Huge stars will go supernova and implode and form what we call stellar mass black holes. We know of many of these. We can observe these combining because of the gravitational waves that we've observed. The other kind of black hole that we know of is supermassive black holes. Now, aside from being a pretty good Muse song, it is also what we think is at the beginning, or rather the middle of every galaxy. Whichever galaxy we look at, including these early galaxies that James Webb is observing, we find these supermassive black holes. So do we think these supermassive black holes were there first, in which case the galaxies formed around them? Or is it something that came afterwards and supermassive black holes kind of formed rapidly as these massive stars died and came together? Because these earlier stars will have been so monumentally massive, they will have all formed black holes when they died. So maybe they all coalesced and then galaxies formed around them very rapidly. Or this third one here in pink, this idea of so-called primordial black holes is something we haven't observed yet. Maybe in this whole maelstrom of stuff happening in between 10 to the minus 36 seconds after the Big Bang up to maybe a second or two after the Big Bang. There could have been overdense areas there that formed black holes as well, in which case we haven't seen them, or maybe supermassive black holes were formed in that area. These are things that we've not been able to see yet, but we will be able to use future iterations of LIGO and future iterations of measurements of gravitational waves to hopefully see some of these things. But we're not quite sure. But we know that all galaxies have supermassive black holes in the middle of them. We don't know if they came first and the galaxies formed around them or the other way around. The other idea is one of two dark things that I'm going to talk about today: dark matter and dark energy. So dark matter may have caused the structure as well. And this is the theory that we kind of err towards a little bit more. In reality, it's probably a combination of both black holes and dark matter. But we think, and we observe this kind of scaffolding in the universe upon which galaxies are hung. We think when we look out on these vast cosmic scales, the universe has this kind of web of dark matter. What do we mean by dark matter? Well, dark matter isn't something that is easy for us to observe and measure that just happens to be dark. The word dark means we have no idea. We don't know where it is. Dark, in this sense, is just a fancy scientific term of saying, so we don't really know where it is. It is observable by virtue of not being observable in any way apart from the fact that it affects things gravitationally. We know it is there because the rest of the stuff we can see behaves a bit strangely. And we only really discovered this in the last 30 or 40 years. It interacts gravitationally, but it doesn't interact via any of the other forces that we know just yet. We haven't seen any evidence of it. There is evidence of dark matter gravitationally, so we know it is there. So one of the key pieces of evidence that we have is the way it affects the stuff that we can't see. And the stuff that we can see is what we call normal matter, the stuff of stuff, as Carl Sagan said, right? Baryonic matter, atoms, dust, stars, people, all that stuff is affected by dark matter. And we have one person really thankful for this, Vera Rubin, who passed away just under 10 years ago. She was observing galaxies, lots and lots of galaxies, and she was measuring how they rotate. The expectation, based on traditional physics, Keplerian physics, Johannes Kepler, says that towards the center of mass, things spin around and orbit fast, like they do in the solar system. Mercury goes around very quick. Way out in the sticks, Neptune goes around slower. We'd expect the same thing with galaxies. Stars close to the center of mass of galaxy should go around fast. Stars further out, more diffuse, fewer stars, should go around slower. What she saw, and what this nice looking graph from the 70s tells us, is that is not the case. In fact, they are stars in galaxies towards the exterior of galaxies are moving far too quick by an order of magnitude. They are not getting slower. It's basically what we call a flat rotation curve, and things are not moving in the way that we would expect them to be moving, which suggests basically that there is an awful lot of additional mass in every galaxy. It's not just one galaxy that we saw this in. All galaxies are doing this. We can do an undergraduate physics experiment. In fact, I was working in the labs at the University of York today with some undergraduate students, mapping the positions of clouds of hydrogen in our own galaxy at successive distances and mapping how fast they are moving. And we can repeat this experiment and see that our own Milky Way is doing this as well. So we've got dark matter here. Something invisible, dark matter, is holding the galaxies together in a very meaningful way. And we think it exists in this kind of dark matter, invisible halo, if you like. Galaxies are embedded in these halos. We can't see the dark matter, we can't measure it apart from how it affects the speed of the stars, but we know it is there. If it wasn't there, the stars would be moving differently. We think, ignore the dark energy for a second, we think for this to be true, there needs to be about 5 times more dark matter than there is ordinary matter, right? 5 times more stuff that we can't see. This ratio is kind of upsetting because it means, again, just ignoring the dark energy for a second, all the stuff that we can see and enjoy, the pictures that Hubble takes, only accounts for about, I don't know, what, 5% of the stuff in the universe. Dark matter about 25%, dark energy, which we're going to come to in a few minutes, which is even more depressing, is going to account for the vast majority of everything else, right? So this discovery was kind of mind-blowing. There is other evidence for this as well, right? We see when we look at these huge clusters of galaxies, we can measure the gas that these galaxies are enshrouded in. And its positioning relative to these clusters of galaxies tells us that there's dark matter. If it wasn't, then the gas would be localized much closer to the galaxies. The fact that it's more nebulous tells us that it is more diffuse and there's something vast and heavy holding it there. This is a picture in different wavelengths. We're looking at a galaxy cluster of maybe 100 or so galaxies. This is a real picture combining X-ray wavelengths and visible wavelengths. The gas in blue is emitting X-rays. The galaxies that you can see there are emitting visible light. So we can see the gas, and it is not positioned where it should be if dark matter didn't exist. So for that gas to be where it is, dark matter needs to exist. Same thing with the bullet cluster. This is two clusters combining over the course of what must have been billions of years. We can see the wavelengths shifting, we can see redshifts, we can see these galaxies moving towards each other, and they've combined, and the gas is slightly different temperatures in different regions. The passage of that gas through the different galaxies, as we can see on this image again in X-ray and in visible light, would be different if it wasn't for dark matter. So we can see things like galaxy clusters colliding in an interesting and strange way because of dark matter existence. One of the more beautiful ways that we can see dark matter, or rather glean its existence, is because of this chap. So he predicted, with his theory of gravity, general relativity, that space-time is curved. Slightly different to Newton. Newton says that gravity is due to the mutual force of attraction between two objects. Einstein said something with mass warps space-time. If we're looking at simple things like planets going around the solar system, it doesn't make a difference whether you use Einstein's or Newton's. But on grand scales, we know that if Einstein's is true, vast things like galaxies and clusters of galaxies will warp space-time to a sufficient degree that light should bend. We see that happen. This is a real photograph, again, in X-ray and visible light. What we're seeing here is a group of galaxies. So we are seeing two galaxies here, the eyes, if you like. What we're seeing around the edge, these arcs, are an amplified image, if you like, a magnified image caused by the warping of space-time of these two massive objects. So the two eyes are foreground galaxies. The arcs are images of galaxies that are much, much further away, that are being contorted and bent by the gravitational lens. Einstein himself never believed that we'd be able to see this. He didn't think that our telescopes would be able to resolve such things. He predicted it mathematically in his equations, but he didn't think it would be possible to see them. We do see them, and we find these beautiful things called Einstein rings. Basically, where just the overlapping of a galaxy or a galaxy cluster is so perfect that it blocks the light of something much, much, much further away and amplifies it and contorts it. Because of this effect, we can predict, again, we know based upon the light from these galaxies, the visible light, how much stuff, ordinary stuff, is in these galaxies. And the warping is far too great based upon just the stuff that we see. There has to be dark matter there. An interesting aside here is we can use this effect to see some of the earliest galaxies as well. And James Webb is looking at some of these arcs from these gravitational lenses because it magnifies these early galaxies that are much, much further away. So we're using gravitational lensing as a way to see even further into the past, which is kind of mind-blowing. We're using the galaxy itself as a piece of equipment. We still don't know where it is, but we know it's there. Some theories, the most common theory, suggest that it is a WIMP. Astrophysicists like an odd acronym, weakly interacting massive particle. Basically, it's some part of the standard model that we just don't know where it is yet. Lots of efforts have gone into trying to find it. We have got form in this, by the way. So we predicted the existence of what are called neutrinos before we found them. We then found neutrinos, these tiny, very fast little objects whizzing through space, billions of them passing through our bodies every second. We found them, we've observed them, we predicted them first. A lot of effort and money is going into trying to find what dark matter might be. The strongest theory at the moment is that it's a particle that we just don't know where it is. So, with that in mind, we know galaxies came into being probably around the structure of dark matter, although we don't know what dark matter is, probably around huge black holes as well, although we don't know what order those black holes were made in. So what is the current configuration of the universe? Well, on the smallest scales, we've got galaxies themselves, which form into groups. Our local group, in a few billion years, will probably look something like this. This is a very compact group called Stephen's Quintet. This is a photograph from Hubble. This is 4 or 5 galaxies very, very close to each other. These are gravitationally bound. They're going to combine at some point in the future, just like ours will. Our local galaxy group is not very romantically named the local group. There's about 50 galaxies in it, the nearest of which is Andromeda. We're going to merge with Andromeda in about 4 billion years. We'll see a video of that in about 10 minutes, CGI video of that in 10 minutes. The next nearest is Triangulum, very beautiful galaxy. We'll merge with that in about 10 billion years. And then beyond this, the larger scales, we have what we call clusters. So this is where we've got maybe hundreds, if not thousands of galaxies. These are the largest gravitationally bound objects in the universe, if you like. So this is the extent to which gravity starts to have its final hurrah, if you like. Beyond this, gravity isn't strong enough to hold things together. We'll see why in a second. So we're part of the Virgo cluster. We're on the outer reaches of the Virgo cluster. Beyond this, on the grandest scale, we have superclusters which form along these filaments that we saw earlier on, these big webs. In between these big filaments, we've got what we call bubbles, where there are maybe 5 to 10 times fewer galaxies in them. So we've got big filaments of galaxy clusters, groups, superclusters, in this big forming intergalactic universal structure, if you like. On this scale, it looks kind of forming. If we map everything that we can see, then it looks kind of like a big sponge. And these are trillions upon trillions upon trillions of galaxies. What do I mean by gravitationally bound on this scale? I said that galaxy groups and galaxy clusters are gravitationally bound, superclusters are not. What we mean is the universe is expanding, and beyond galaxy clusters, gravity is just not strong enough to start to bring things together anymore because they are getting pushed apart too quickly. What is doing that is the other dark thing, this other big unknown, dark energy, which is the kind of source of the expansion of the universe, if you like. A nice analogy of this would be if you have a balloon and you put an ant on the balloon and the ant walks around the balloon and you start to blow it up, the ant would see the balloon blowing up, but it wouldn't know why it's blowing up, right? So the universe is expanding and we don't know why it's expanding. Someone's just pumping air into it constantly and it's just getting bigger and bigger and bigger and we have no idea. The force of dark energy surpasses that of dark matter, broadly speaking, on these vast scales. So once we get past a certain threshold, anything that is not gravitationally bound never will be. That has repercussions in the far distant future, because anything that is gravitationally bound will eventually together. But because of the expansion of the universe, beyond that, things are just going to keep getting further and further and further apart. It's like a tug of war, if you like. We don't know what it is, like I said, no clue, none, zero. There are some hypothetical ideas, one of which is this idea of like a fifth force, almost like negative pressure, right? So we've got the 4 forces that I briefly alluded to earlier on, this other idea of something unknown injecting energy into the universe and causing it to expand. We can't measure it. We know that it exists. We know that the universe is expanding and it is responsible in terms of energy density for about 70-80% of the entire energy density of the universe, and it's only getting more and more, right? As the universe gets bigger and bigger and bigger, the amount of stuff in the universe isn't going to get any bigger and bigger and bigger. That is fixed. That was put there at the Big Bang. No more stuff is being made. But the universe is getting bigger, which means more energy is getting pumped in. We don't know where it's coming from. An interesting other idea is Einstein's cosmological constant. Now, Einstein, as with Fred Hoyle, didn't really like the idea of an expanding universe. So in his gravity equations, he put this fudge factor in called the cosmological constant, which allowed for a static, unchanging universe. As with Einstein being correct all the time, even by accident, this cosmological constant very nicely mathematically describes everything we observe with dark energy. So we use his cosmological constant now, this accidental fudge factor that he put in there, as a nice mathematical description of what we think dark energy might be. But we don't know what it actually is. Things like string theory, things like quantum field theory can tell us a little bit more about how we might describe these things. But in terms of what it is, we are no closer to identifying what it could be just yet, I'm afraid. We just know that it's happening, and we know that it's making the universe expand. So that is where we are. We live in a universe that's about 13.8 billion years old, lots of galaxies with lots of structure. It started in a Big Bang, progressively got larger, and it is expanding, and it is expanding more and more and more because of dark energy. What happens in the future then? So for the last 5 minutes, I'm going to talk about the 3 potential routes that we might take. As I said, fortunately for us, life is finite and we won't see any of these things, which is probably for the best. There are 3 options, only one of which is legitimately feasible given modern physics. One of the which is a big crunch, the other one's a big rip, and the other one is just kind of infinite expansion. Not long ago, the idea of a big crunch was more popular. So we'll do that one first. So the idea of a big crunch is the idea that over time, dark energy, which is causing the universe to expand, would actually weaken. And as it does, gravity, which is mostly apparently governed by dark matter, would become stronger and stronger again, and things would stop expanding and eventually compress and come back down again, almost like a balloon blowing up and coming back down and blowing up and coming back down. So in this idea, gravity ultimately dominates, expansion ceases and comes back down, and we almost have this idea of a cyclic universe, right? It is, in terms of being poetic and pleasant, it almost seems like out of the three of them, this is the more appealing. This idea of a never-ending cycle of expansion and contraction, right? It seems more logical, and this was the more favored idea until about 20 years ago. However, there is no evidence that this is going to happen. What evidence tells us is that dark energy is not getting weaker. In fact, it is just going to continue to expand. That leaves us with two options. One of them is, what if dark energy gets even stronger? What if dark energy becomes so strong that it eventually strengthens and strengthens and strengthens to the point where even things like galaxies can't hold themselves together? Over time, even things like ordered structures like stars and people and atoms can't hold themselves together. Gravity stops functioning. The strong and weak nuclear force stops functioning, and the entire universe will eventually rip itself to shreds. This, mercifully, is also probably off the table. What we see in terms of the expansion of the universe is dark energy seems to be a fairly constant thing. It isn't changing in its prowess, if you like, over time. It's certainly not giving any indication in terms of the expansion of the universe that this is going to happen. Which leaves us with one final option, which maybe might be the most bleak of them all, really, kind of sad. This idea of a big freeze, right? This idea of everything getting colder, better known as the heat death of the universe. What this means, basically, is the Hubble constant will maintain its same value forever and ever. The universe will continue to expand and expand and expand. Things that are not gravitationally bound will never be gravitationally bound. Those that are will coalesce. And eventually, when all the hydrogen has been used up, star formation will stop. And then when all the star formation stops, those dead stars will cool down. And what will happen, basically, is the universe will cool. This is going to take a very long time. This is the one that we think is going to happen, by the way. This is the one, at the moment, that modern physics tells us is the trajectory that we're on. Remember, we were talking about those big numbers with lots of zeros in them earlier on. We think this, the end point, well, not the end point of this, but the point where any meaningful structure in the universe exists will be about maybe 2 Google years. So 2 with 100 knots after it, right? So a very, very long time. The way we think it's going to happen is the era we're in now is called the stelliferous era. That is, there are stars forming, continuing to form, evolving, spewing out stuff, and allowing new stars to form. Eventually, as that happens, continues to happen, the hydrogen will eventually get used up, and there will no longer be the potential for stars to form. At the same time, all these gravitationally bound things like galaxies, galaxy clusters, and galaxy groups will coalesce. And we know, based upon the trajectory of the Andromeda Galaxy, in about 4 billion years' time, Andromeda and the Milky Way will merge together to form a super galaxy, a big elliptical galaxy. As time goes on, all the other galaxies in the local group will do the same. We'll just form into this big elliptical galaxy. As that is happening, everything else is going to get further and further and further away, until eventually we won't be able to see any other galaxies anyway, because everything's just going to be so far away. Any life that evolves in these galaxies, these big super galaxies that have coalesced, won't know that there was a cosmic microwave background, because the universe will have expanded to the extent that it's so cool that they can't see it anymore. Any galaxies that existed so far away will have fallen off the observable trajectory, if you like. They will no longer be visible, and they will just live in a dark, horrific void, which is not going to be very pleasant for anyone who evolves in about 15 to 20 billion years. Beyond this, the last stars that will exist will be red dwarfs. These are tiny, tiny, tiny stars. These are the things that just churn through hydrogen very efficiently for potentially 100 billion years or more. These will be the last ones to keep forming, and these will be the last ones to die. And when they do die, we'll end up in the degenerate era. That is all the stuff that is left over from these dead stars. So when stars die, they leave behind certain things. They leave behind white dwarfs. That's what our sun will eventually leave behind. Bigger stars leave behind neutron stars. Even bigger stars leave behind black holes. When that has happened, when this has happened, when the final star has died, we'll just have a universe full of these things. From about 10 to the 40 years onwards, up to about 10 to the 40 years, I should say, this is what we'll be living in. White dwarfs cooling down, cooling down, cooling down to the extent where eventually the material within them almost does the inverse of what we talked about at the beginning of this. It's no longer hot enough or energetic enough for particles to maintain those bonds anymore. The particles start to break down. Protons start to break down into quarks. The energy levels drop and drop and drop until everything becomes cooler and cooler and cooler. The structure that exists in the universe breaks apart, order into disorder. After this, from about 10 to the 40 years to 10 to the 100 years, all that will be left will be this diffuse sea of cold, dead material and some black holes. And even the black holes will die. So we think, based upon this chap, Stephen Hawking, that black holes in such a vast, prolonged timescale will evaporate as well. There's this thing called Hawking radiation, which tells us that eventually information that passes into a black hole will evaporate out of it. So in these timescales, even black holes won't survive, which leaves us at the end where we're at a state of what is called maximum entropy. Thermodynamics in the universe gets its stranglehold and wins eventually. It doesn't like order. It doesn't like things to be together. It doesn't like humans to exist. It doesn't like planets to exist. It doesn't like stars to exist. Eventually, it will win, and all the atoms will break apart. All the black holes will evaporate, and what will be left will be a cold, desolate, cold void forever and ever. Thanks.
That certainly put everything into perspective. Have we got any questions from
Sorry for the bleak ending.
Then you?
What generates dark energy?
But
What generates dark energy?
we don't know. So we know that it is there. As with dark matter, we know that it exists, but the driving force behind it, if you like, is one of those unknowns. One of the popular theories behind it is field theory, quantum field theory, this idea of negative energy, this idea of, I can't really describe it, this idea of energy popping into existence at every point in the universe. Right? I agree. So for people on Zoom, the response was this, and I agree. We don't know what it is. We don't know what is causing it. We just know that it is driving the universe to expand, and there's something doing it. We can't measure it. We can just measure the effect of its expansion. We don't know what the energy is. It's just a name. It could be anything. We see the universe that we see, and we can measure it. What goes on beyond the observable at the moment, who knows? We have chipped away and chipped away and chipped away for 100 years and discovered things that we predicted. And it is very possible and plausible that in the next 50 to 100 years, we will have the capacity to understand what is causing this. But at the moment, we just don't have the observational capacity to do it. Things like the Large Hadron Collider is allowing us to find out about these hidden particles. We're very close probably to finding out what dark matter might be. The next step will be finding out what dark energy is. But at the moment, we don't know where it is.
A long time ago, Galileo, the Catholic Church, got very upset when he sort of made scientific discoveries. How did the Belgian priests get on when you started doing this?
Very well. So the question there was, how did the Belgian priest Georges Lemaitre get on when he suggested the idea of a Big Bang? Well, there's a very famous photo, if you Google him, he's got his arm around Albert Einstein. They were good friends, and I think the 1930s were a little bit more of a kind of happy period for people who suggest such things. He was a renowned scientist as well as a Catholic, and there are pictures of him milling around with the Pope as well as Einstein, and I don't think there was any problem at all. I think it was just kind of a nice thing. I will say the ideas at the time were a little bit kind of not well approved of. It took about 20 or 30 years for the Big Bang Theory as it is to take hold. So it wasn't so much the fact that it was a priest that was a problem. It was the fact that it was talking about things that weren't really approved of at the moment. The steady state theory that Fred Hoyle liked, and the steady state theory that Einstein liked as well, to be honest, still held sway until the 50s or 60s. So it was less popular because his ideas were a bit strange rather than because he was religious.
Paul?
I think you're much better than Brian Cox, by the way.
Oh, thanks. Don't have the hair though.
Be destroyed, it can only be transferred from one form to the other. And there's all this dark energy being pumped into the universe from somewhere magical.
Yeah.
How come the energy of the universe isn't full of infinite energy rather than being cold and dark?
Well, that's a good point. So the question there was, at the end of the universe, if the matter is all dissolved and all that's left is energy. I mean, that's basically, you've described what will be the case. It'll just be, but it's not an energy in the sense of electricity being an energy that we can kind of physically grapple hold of or mentally grapple hold of. The energy that is being injected into the universe isn't something that we're familiar with, right? The first question there was asking what it is. We don't know what it is. It might be more of a fifth force. The idea of an energy is almost a misnomer, really. It is something causing the expansion of the universe. It might be a force, it might be an energy, it might be antiparticle, it might be this something unknown that we don't know. But at the end of the universe, all the particles will have just gone cold, and that mass energy balance of the universe, E equals mc squared, energy and matter, as you rightly said, are equatable. It will just be cold and dead, and there will be energy transferred. That isn't to say sometimes things might not bounce into each other at the very end of the universe, and a little particle might not just nudge another one. Some things might happen, but it'll be very rare. But yeah, we don't know about dark energy. Who knows?
Is there anything to suggest there are other universes that the energy might be coming from other universes?
Yeah, so there's an awful lot of I wouldn't say research, but there's also an awful lot of conjecture and reasonable discourse about the idea of our universe being one of many, right? There's some famous physicists who've dedicated their lives to things like string theory, which postulate the existence of dimensions and physics beyond the realms that we can see. There's a famous meme around this. It's the first page of a book about string theory. First chapter is called Observational Evidence for String Theory. The first line is, there is no observational evidence for string theory. But the idea of there being other or something else that we cannot see is certainly very reasonable, right? It's taken us, we talked about Galileo, 500 years to get from Galileo's physics to our modern physics, and then he would not recognize the universe that he sees now in terms of what we have been able to measure. Things like dark matter, dark energy, even though we don't know what they are, the idea of them is mind-blowing. The idea of there being gravitational lensing, the idea of the gravity itself being a warping of space-time, all these are just mind-blowing ideas that were just new in the early 20th century and still new now. So the idea of something new coming along, like the idea of bubble universes is another one, or the idea of there being additional dimensions governing the physics that are taking place in our universe is, although it's odd, people are dedicating a lot of time to mathematically describe things, but we don't know like if it's the case or not. But yes, to answer your question, it seems reasonable that there must be something additional there that we're not measuring, whether or not it is additional universes or additional forces, additional dimensions, additional levels of physics that we've just not measured yet. Who knows? But bubble universes, or the idea of there being another universe, right? Us being the only universe, it's hard to comprehend as a human being, this idea of there being a beginning, but then nothing before it, or there being just an everlasting ending of dark, desolate, cold. What happens either side of those things? How do we religiously or philosophically grapple those things? Well, we can try and describe mathematically other ideas, but at the moment we don't know what those could be.
But that, and then you, yes. Go ahead.
It's fascinating to hear that so many people have spent all their lives working out exactly when this Big Bang started to a fraction of a second.
Yeah.
But you did say that at the Big Bang, everything came into existence, including time. So do we assume that this time suddenly becomes a constant, such that you know what a fraction of this bit of time is?
What's the state? So the laws of our universe don't say that time has to go forward. So we are basing our ideas of this very early period in the universe based upon what we see now, what we see all the way back to the cosmic microwave background. We haven't seen any change in what time is and how it behaves in the universe. Whether or not it might have been different in the early universe, whether or not there might have been different laws, not just with time, but with the laws of physics themselves in this early universe. Because we can't see it, we don't know if that is the case. We're just assuming that the universe came into being fully formed in terms of the laws that govern it, including time. I don't know if that answers your question or not. We don't know whether or not. Sorry.
Yeah, no, so.
Question. Recently, I had and the theory in ancient Hindu Vedas, the world, there's a big bang, and the world comes, and billions of years goes away again. Then it and comes, and I'm just wondering at the end of the world we're talking about that. I mean, they talk about billion years, is somehow the earth comes back to zero again and start back again.
This whole cyclic nature of the universe that is appealing, right? Like that was one of the reasons why the big crunch theory, this idea of dark energy losing its power and everything collapsing back gravitationally again, was such a popular one, not just because of and then starting again, right? It seems observationally that won't be the case, it's just going to fizzle out, sadly. But there is a lot of parallels between, especially like Hinduism and religion from thousands of years ago, describing aspects of the universe that we observe now in a very kind of, albeit poetic, but meaningful way. It's almost like it was predicted. It's a description, but it's a description that means something to people. And it's nice to pin some of these things onto the observations that we can make, but whether or not there's a connection between them or whether or not it's just a coincidence and a poetic license that people have taken to describe things, who knows? But like, yeah, the early, like you say, Hinduism particularly is quite adept at this. But I think there won't be, based upon physics, I don't think there will be a big crunch, sadly.
I'm thinking about the capture of light by black holes and gravitational lensing. Why are these not evidence to say that the photon has mass?
The photon having mass is an interesting question. It has momentum, right? So it moves and it affects us. If you go out on a hot day, you will feel the heat of light touching your skin. It's got momentum, but it doesn't have mass. If you never get a photon that is traveling less than the speed of light. It's just a strange and interesting quirk of physics. They're affected by gravity because they have momentum, but they don't have mass. They're massless particles. This is what they're. I know. Kind of twisted, yeah. It's the wave particle duality of these things. It behaves as a wave as well as a particle, but a particle without mass. Another interesting thing, this is just completely moving aside from your question, but an interesting pub quiz fact again is photons, these particles of light, don't experience time. So the light that was emitted from the cosmic microwave background 13.8 billion years ago, when it reaches our antennae after this 13.8 billion years, because at the speed of light, time does not exist, those photons have not experienced time. So the instantaneous point that it leaves the atom at the point of the cosmic microwave background is the instantaneous point that it reaches the feed horn. When the light leaves the sun and hits our retinas is instantaneous for the light itself. Time does not exist for photons, time does not exist, but it's traveling at the speed of light. Physics tells us at the speed of light, time doesn't exist either.
Well, I mean, can't be available for questions. But I would like to ask Jim Drive to give our vote of thanks.
Sorry.
Yeah.
I'll come up here so I'm not a voice from the distant past. What a great talk. It's just terrific. I would ask for your sympathy because I have O-level arithmetic. I've struggled to get higher maths, but managed, and I have been tasked with taking notes for the minutes. So I hope it's, and my connection with astrophysics is minimal. It is that when I was a first year student in Edinburgh University, the Vice Chancellor was Edward Appleton, who had won a Nobel Prize for his work in astrophysics. I mention that because Edward Appleton went to the same school as Thomas Shunt, sorry, in Bradford. A little known fact. Did you know that?
I did not.
Well, so I'm glad I've managed to enlighten the speaker on something. The talk has been about speed and our concept of speed and time. And it's very relevant to my experience of the talk, because this hour passed in it's the only time in a long time when the speaker said, and in the last 5 minutes, and I thought, what, already? It was just amazing. The other thing that we've all taken in, which I would comment on, is the pictures. They were not highlighted, they were there in the background, but they really helped. The big sponge is a lovely way of conceptualizing all this stuff that's going on. So thank you for that. And the other great thing that is unusual is Tom's willingness to say we don't know. And you were struggling, you know, there must be something, and you tell us what you know, you tell us why you know it, and there it is. And I really like that. So it was super, and I really think, I feel that you've left me with a concept of the big picture, how all these things, the people, the concepts, and the instruments indeed fit into the story. And I'll go away thinking that. But when I go back to tell my wife, it will be a little bit like somebody Billy Connolly tells tells the audience, you know, at the end of this, you'll go back and you'll say that was great, and your wife will say, "What did he say?" And I'll say, I don't know, but it was great.